When we talk about an object's motion, we are interested in three quantities: its position, its velocity, and its acceleration. To obtain these quantities and see what they mean, we start by defining an origin, a reference point. The position vector, which we call r, is the arrow that points from the origin to the object. As the object moves around, the position vector generally changes, and so we say that the position vector is a function of time. The velocity vector is another arrow which tells us about how the position vector changes over time. Specifically, it is the rate of change of the position vector arrow with respect to time. If, over time, the velocity vector of an object is changing, we say that it is accelerating, and we define another arrow, the acceleration vector, which tells us the rate of change of the velocity vector with respect to time. Each of these vectors are arrows with a size and a direction, which are described as functions of time. Using these equations here is a simple exercise. If you have the position vector as a function of time, you can differentiate it to find out the velocity vector. And if you have the velocity vector, you can differentiate it to obtain the acceleration vector. So we know how to go from the displacement vector to the velocity vector, and likewise for the velocity to acceleration. But what about the other way? What about if we know the acceleration vector? How do we find out the other two? We do so by rewriting the above equations in an integral form as follows. Now, if we know, for example, the acceleration vector as a function of time, and we wanted to know the velocity vector, we would integrate. Now, there are some things to notice when we are integrating. One is that if we do the integral like this, an indefinite integral with no limits, we know we have to include the plus c term that you are familiar with. This means that our description for the velocity vector is not complete because we have this unknown constant in there. Figuring out the value of this constant is very similar to what you have done many times with graphs. We need to evaluate the velocity function at a point that we know, so we can find out the constant. For example, if we were told that when the time is 0, the object has 0 velocity, we can plug those numbers in and deduce that c must be 0 in this case. As I said before, all of these vectors are functions of time, and when we have functions, we must be aware of their domains. If this is the velocity vector for an object as a function of time in this domain, then differentiating it gives us the acceleration vector in the same domain, and integrating gives the position vector in the same domain. For times outside of this domain, these functions do not describe the object's motion at all. When we integrate indefinitely without limits, we obtain the functional form of a vector. What about if we use limits and do a definite integral instead? Like when we do a definite integral to find the area underneath a curve, the result will be a number, a value. What this value tells you is clearly not the functional form of the vector of interest, but instead how much this vector has changed in the specified time interval. For example, if the velocity vector is given by this function, and we integrate it between times 1 and 5, we are finding the change in the displacement vector between times 1 and 5. It may help to realize that this will also be the area underneath the velocity time graph between times 1 and 5. The same can be said if this were the acceleration vector and we wanted the change in velocity between two times. Knowing the difference between indefinite and definite integrals can be very helpful when solving more complicated problems.